So we are live. We are back. We are back. We are live. It will be part three. Part three. I will stay all the night here in France. It's 9 in the p.m. and I will stay all the night and we'll learn AI. We'll learn machine learning. So back live. Back live. So let's go. Let's go. Let's go. Let's go. Let's share my screen and ready go. Ready go, bro. We are here. We learn the anatomy of we have learned the anatomy of the data set, So we have learned about feature vector, outcome, column, row. Each column is a person in the data set. Each row is a sample, is a category of in the data set. Like for example, here we have a data set about diabetes, and there is pregnancies, glucose. It's each column. It represents each a category of data. Each row represents a person of data. We have the feature vector, and we have the target vector. We have the feature matrix, which represents all the feature vectors, and we have the target vector, which represents all the outcome, all the label, the outcome, the label. Yeah, let's go. Let's go. We'll continue that. Okay, this is known as the feature matrix, and all these are the vector, the targets of the label. Okay, let's kind abstract this, abstract all of this to a piece of chocolate, to a piece of chocolate. Okay, let's let's abstract all of this to a piece of chocolate. Okay. What? Okay, okay. Abstract it to a piece of. You know what? I will call it the metaphor of chocolate. Metaphor of chocolate, and we will use chocolate as a metaphor for data. Incredible. It's here. It's nowhere else. It's nowhere else. It's here that we learn that. Let me see though. Okay, it's working. Okay. Okay. We have all the numbers that represent our X matrix over here. We have all the numbers that represent and the value that our output y. Okay, we have all the number that represent our X matrix over here at the left. We have all the number that represent our X matrix over here at the left, and the value or output y are at the right. Okay. Oh, okay. Okay. Each of these features. What is this? I will answer later. We'll answer later on this. Okay, let's go. Each of these features. Okay. Okay. Each of these features, like this. So the chocolate bear here represents this kind of information. Okay, we agree like that. Each of these features, um, when we represent them as a chocolate, when we represent them as a chocolate bar, it's like this. It's like this. But as data, it's things like this. But as data, these are things like this. So each of these features that we see, each of these features that we see as chocolate here, okay? Each, okay, each of these features, when we represent that as chocolate bar like this is our feature vector. This is our feature vector, okay? We plug this into the model. We the chocolate bar is our feature, is like our feature vector that is like this. The chocolate bar is like our feature vector, and we plug it into the model. Okay, and we plug this into the model, and then the model is making some sort of prediction. Okay, the model is making some sort of prediction. Okay, it's basically the algorithm of the model in a, I think, supervised learning. That's what we're learning here. We are learning supervised learning. Okay, and then the model is making some sort of prediction here, and then we take the prediction. Then we take the prediction, and we compare it to, our target in our data set. And then whatever difference there, we use that for training. Whatever distance there, we use that for training. Because if we are really far off, okay, whatever difference between the prediction and what we compare to our data, and the comparison to our data set, we use that for training. Okay, I can say it like that. Okay, training. So we compare the prediction of our model. So it really comes by, it comes back to what we have seen previous in the previous live, where we have seen the different steps to make a model in machine learning. One, you collect the data. Two, you good, you split the data. Three, you define the model architecture. Four, you train the model. um, um, Five, you evaluate the model. Six, you fine tune the model. So really, what we're talking about here, when we compare the prediction of the model versus our data, we really compare. We are really trying to evaluate the model to really fine tune the model even further. So, alors, So and then whatever difference that we use that for our training, fine tuning the model, CF, because I think I want to reference this part because it's such a good part. How to make the model learn in machine learning. CF, how to make the model learn in machine learning. How to make the model learn in machine learning. Let's go, let's go, let's go, let's go. Boom, insertion, boom, how to make the model learn in machine learning. Boom, reference. It's so good. Google document is so good, bro. I love Google document. I do everything in it. Okay. And then whatever that we use for whatever that we use that for training. Fine tuning the model slash evaluate the model. Mm. Okay, it's good. Okay, fine tuning the model slash evaluate the model. Okay, okay. I fine tune or I evaluate. And oh yes, yes. I want to say that. I want to say that. Okay, what we do here is we um, we take the prediction of the model and we compare it to our data. And we will see a difference. We might see a difference in prediction, and that we will use. We might see to fine tune the model. We will see a difference in prediction that we might use to fine tune the model. To fine tune the model. Okay. Because if we are really far off, we can ask our model to make it closer. I think to make it closer. Okay. I think we have to write code for that. I mean, we'll not ask with natural language, hey, model, can you make it closer? Can you make your prediction closer to the real data set? Make, but, but if we are really close, like meaning the prediction and meaning the prediction of the model and our the model and our real data are close. Um, we we say to the model, keep doing that. Keep doing you, bro. Okay. So so this is our entire bar of chocolate. This is our entire bar of chocolate. So let's say this bar represents all the data we have access to. Do we want to feed this entire thing into our model and use that to train our model? So let's say this bar represents all the data we have access to. Do we want to feed this entire thing into our model and use that to train our model? Okay, she's talking about the fact that you should split your data. And again, okay, splitting the data. Of course, splitting the data, CF, splitting the data, CF, CF, okay. Ooh, can we really be like, okay, um, um, which is the thing I want to say? Oh, I forgot this one. How to make the model learn machine learning. Let's see if it's working like that. How to make the model. No, it's not working. CF. Let's do it the old way. I refer to that chapter, and like if you want me to share my notes, I need 1,000 likes on the YouTube video, and I share my note for 1,000 likes. I had to make the model learn in machine learning. Boom, boom, boom. Okay, your intuition may be to feed the whole data set into our model. Your intuition might be to feed the whole data set into your model. But 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 when we are building a model, we don't want to use all of our data. In fact, we want to split up your data. TF. I reference this chapter a lot because you want some sort of metric to see how a model will generalize. So, splitting. So we split so we split up our chocolate bar, um, which is our data set, which is a metaphor for a data set. So we split up our chocolate bar. So we split up our chocolate bar into a training data set, validation data set, and the testing data set. Our training data set is what we are going to feed into a model, and this might give us an output. Okay. Okay. So what she's talking about is that we will split the data in three. We'll have a training data set, a validation data set, and a testing data set. It looks like it will be like 60%, 20-20. Like if we really look at the proportion, it looks like that. So our training data set is what we're going to feed into a model, and this might give us an output. We check it against the real output, and we find something called the loss. Okay, let's go. Which we will talk about in a second. Okay, so we will use our training data set that will feed into the model, and this will give us an output that will okay. We can think of the loss as a measure about how far. Okay, we can think of the loss as a measure about how far off we are. How far off we are. Put that into number value, and then feed that back into the model. And that's where we are making adjustment. Okay, so the model. Okay, so it means it looks like there is a feedback loop where we make adjustment training set where it looks like there's a feedback loop where we see the loss and we give it back to the model, and the model is trying to figure out is trying to figure out a way to adjust this loss so it's as we want it. This process is called this process is called training. Now we also have this validation set. is we feed it into the model. And we can actually access the loss on this validation set. Because we have the real answer and this. Okay, I'm really trying to figure this out here. Now we also have this validation set. So this validation set, we feed it into the model and we can actually access. Okay. Okay. Here I can type validation set. Okay, here, boom. Now we also have this validation set. We feed it into the model and we can actually access the loss on the validation set because we have the real answer. Okay, validation set is not used to train, but we have the data and the real answer, so we can figure out the loss. And we have the prediction, and we can see how far off we are. Okay. The validation set is used as a reality check during after training to ensure model can handle and see data. Because remember, up until this point, our model, okay, is used as a reality check after training to ensure model can handle unseen data. Okay, okay. Unseen data validation set is data. Validation set is data that the model has not seen. So it's an accurate test to see if the model is accurate. The model is if the model is accurate. It's an accurate test based on real data to see if the model is accurate. Okay, I get it now. Yes, indeed, our model has only been trained, has only been trained till now on our training data. Example. Woo! Okay, example. Boom, boom, boom. if I have a bunch of different models. If I have a bunch of different models, and all of these are my validation data set. Okay, models and okay. If I have a bunch of different models and all of these are my validation data set. Okay, let's figure this out. Okay, this is the validation data set. Okay, and these are the predictions. Okay, if I have a bunch of different models and these are my validation set and these are the predictions, okay, she went on another road trying to really explain this, but let's figure this out. Okay, okay, okay. This loss is high. Loss of 1.5 is high. Loss, this loss is high. Is high. 1.5, 1.5 in loss is high. This one is a little bit closer. This loss is, this one is a little bit closer. But this loss is the lowest. This loss is the lowest. We want to decrease the difference between our prediction and our true target. Okay, so the more, so to translate that, we want to decrease the difference between our prediction and our true target. So to translate that, the better the loss is close to zero, the better it is. I don't know why I wanted to close these tabs. Okay, let's go. Between our prediction and our true. So to and okay. So another use case for the validation dataset. Okay. Another use case for the validation data set is to say, okay, model C seems to perform the best on unseen data. So let's take let's take model C. Okay, okay. So to summarize that, what we do is we put okay, we use the validation set, we put in the model, we calculate the loss. If the loss is close to zero, the model that has a loss closer to zero is a good model, and we take it. We take the model which has the lowest loss. Model C is selected. Okay. Once you select model C, once you have selected model C, you can actually go back and use a test set, which again is until down. And we plug that into my untranslated data. Okay, so the validation set is used. Okay, okay. I want to open a new I want to open a new thing here. Difference between differences between the training set, training data, validation data, and testing data. Okay. Um, validation data. I can ask ChatGPT. I will ask ChatGPT just after training data. By the way, these are rice. I don't know how we say that. I think rice cracker, something like that. Galette de riz en anglais. Rice. These are rice cracker. It's really low calorie, so it's perfect to eat while coding. Okay, let's go. Training data. Data that is used to train our model. Validation data. Data that is used to determine which model we will use. Testing data. Testing data. Beware, I think I have the right vocabulary. Data that we use to see if the model can generalize to new data. Boom, perfect. Okay, What is the difference? We will ask ChatGPT. He will tell us what are the differences. Tell us, bro. Tell us, bro. We we're ready for this. What are the differences between the training data, validation data, and testing data? Go, bro. I have no time for this, bro. Go, tell us. Oh, training data is used to train a model. Validation data is used to evaluate a model during the training process, and testing data is used to evaluate the performance of a trained model. The main difference is the stage of the model development. Okay. Okay. It's really good. It's really good. It's really good. Okay. Um, we use different um, different part of the split of data, different during different stage of the model development. Perfect. Perfect. Training data is used to train a model. Validate. Okay. Validation data is used to evaluate a model during the training process. Testing data is used to evaluate the model of a trained model, the performance of a trained model. It's perfect. ChatGPT is live, guys. Period. Period. ChatGPT is live. Training data is used to train a model. Validation data is used to evaluate a model during the training process. And testing data is used to evaluate the performance of the training model. The main difference is the stage of the model development they are used for and their purpose. The training data is used. Oh, I can put it there. The training data is used to learn the patterns of the data. The validation data is used to tune the parameters of the models. And the testing data is used to evaluate the performance of the model. Perfect. Perfecto. Okay, let's go. Once you have selected model C, you can actually go back and test and use our test set, which again is unseen data, and we'll plug that into model. Okay, our test set is unseen data. Yeah. And then we can use that trick, compare it to our target, the final. Okay, that's good. That's what I said. That's what I've said. Okay. The test set is used to check generalizable. The final model is. Okay, let's go. Let's go. Let's go. Let's go. Let's go. Assessing performance. Assessing performance. Okay. Let's go. Let's go. Let's go. Let's go. Let's go. I think it's a title in itself. Assessing performance. Hmm. Yeah. 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 There's a lot of things, huh? It's so different than traditional programming. There is a lot of things to learn in it. It's crazy. You have to think of totally different way. So assessing performance. Okay, matrix matrix of performance. Okay, let's go. Okay, when you're trying to assess performance, there are metrics of performance. I kind of touched on something called a loss function. Okay, assessing performance, the loss function. Loss function is a way to assess performance in a machine learning model. So, we use the loss function to assess performance of a machine learning model. So here we will learn more about the loss function. Okay, I kind of touch of something called a log function, but how do we quantify how different things are? Okay, example with colors, because it's basically that. This, this will probably give us a higher loss than this. And something like that should be a lot for them. Okay, so we use the prediction of the model and we compare it to the test data set or the either the test or the validating data set. I think that's what I understand by that. Something like that should be even higher. I will ask ChatGPT in which part of the training data we use to calculate the loss. No, no. Tell me, bro. Tell me, bro. Uh, I can put it just there. Which part training data we use to calculate the loss? During the training process, the model is typically presented with a batch of training and the loss is calculated on this batch. The loss is measured of how well the model is able to make prediction on the training data and is used to update the model parameters. Okay, so we calculate the loss with the training data set. I think that's what they say. Okay, so what part of the process is she talking about here? I don't understand. You know what? I don't know where I would put that. I might put that at the top of the chapter, like this, yeah. Which part of the training data we use to calculate the loss? Which part of the split? Oh, maybe I have asked it wrong. Maybe I have asked it wrong. Which part of the split of the data of the data we use to calculate? Which part of the data we use to calculate the loss? I don't know. Maybe we'll say something more interesting there. Which part of the data we use to calculate the loss? Tell me, bro. During the training process, in this part of the data. Okay. For to him, it's still the training. Okay. Okay. Maybe. It means that the value of function than the previous one. We just there are a few different types of loss functions. Okay. Okay, let's go. Let's go, let's go, let's go. Okay, let's put our mindset in terms of regression for a second. We are trying to predict a value that is on a continuous scale. Okay, so this might be the temperature of tomorrow. A bunch. If we have a bunch of different cities we are trying to predict, we have a bunch of different points. Okay, so this here, wire real. Okay, okay, let's go, let's go, let's go. We have the formula, bro. We have the formula, guys. So this here, here that we let's you know what? Let's do that like that. That we found in our data set. Wire real. And Y predicted, and Y predicted is the value that our model has output. And what we're trying to do is to find the difference between these two values. And then use the absolute value of that. Okay. So where real, this is the actual value that we found in the data set. Okay, let me do a quick pause though. Yo, bro. Yo, bro. Zelle with pin. What's up, bro? Let me do a quick pause. Let me do some quick. I come back. Two seconds. What up? What up? I'm back. I'm so back. It's crazy. Okay. What we're trying to do is find the difference between these two values, y real and y predicted, and I'll hold this up for every single cities. points in our data set, all the different cities. In order to calculate. So what you do is to calculate, hey, for every different city, how different is our predicted value and the real value. Okay, so to calculate the loss, um, you subtract the predicted value to the real value for all the values, and sum this up. So what to do is for it, and sum this up. This is basically not. Oh, sorry. This is basically it's basically an absolute value function. So if our predictions are really good, if our predictions are really good, oh, this loss becomes really small. If our values are really far off, this becomes really large. There is also another type of loss called L2 loss, which is the same idea. Instead of using the absolute value function, we scale everything. Okay, everything. Okay, understand. So to sum this up, we can say there is two loss function. There are different types of loss function. We can say here L1 loss function. Okay, L1 loss function, and here we can say L2 loss function. Okay, this is also known. Okay, basically here, basically here, instead of of summing up all the differences. You actually square all the differences and then we square those up. Quadratic formula looks like. So here you can see if we are off by a tiny bit, our loss is really small. Let's find out that. Figure this out. Which means that it's good. But by a lot, then our loss gets really big, really fast. Okay. Binary cross entropy loss. Okay. What is that? Binary cross entropy loss. Um, a new formula, bro. Crazy. Okay. Let's think about the classification mindset when we are trying to predict, for example, just two classes. So binary classification. Well, your output, okay, is a probability value. Okay, so in okay in classification, in class, that's what she says. Is in classification, your output is a probability value. Boom. Which is associated with how likely it is. of a class A. If it's closer to 1, class A um, seems to be the more likely. And if it's closer to 0, then it's probably class B. Okay. So in binary cross entropy loss, you are taking the real value times the log of the predicted value. And then adding that with 1 minus the real value times the log of 1 minus the predicted value. I will have to reread these notes, bro. My minus the predicted value. Okay. Sum that up. Sum that up and use a normalization factor. Okay. You don't have to know this. You don't have to know this. Now you don't have to know this. Wow. Specification, your output is a probability value. Yes, indeed. I can consider. Okay. You just have to know that. But you have to know that about loss. Loss decreases as the performance. Loss decreases as the performance gets better. Okay. Um. All this. Okay. 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 Hmm. I should say like loss functions. Loss function. Okay. Accuracy. Accuracy. Is it accurate? Okay, let's go. So one one of the metrics of performance that we can talk about is classification. Accuracy. Okay, one of the metrics of performance that we can talk about in classification is accuracy. Okay, let's say that we have a bunch of pictures here and we want to predict the level. Here on the right, we actually have the actual values. Okay. Okay. Let's say that our model is predicting apple, orange, orange, apple. Okay, let's go. So we got this right, the other right, the other wrong, and the other right. Okay, let's go. Okay. Okay, so accuracy is 3 for 75% or 75%. Okay. If you think about it in English, that makes sense. Sense meaning current amounts is how many how many predictions. How how accurate our model is how many predictions it correctly classifies. Classifies. Okay. Meaning. Okay. Let's go. Let's go. Let's go. Neural network. Neural network. Neural nets. Okay. Let's go. Let's go. Let's go. Okay. Let's go. Up until now, we have talked about what goes into our model, the features, what comes out of our model, what type of prediction it is, we are whether we're doing classification, but we haven't really talked about the model itself. So let's start talking about the model. And that brings me to neural nets. Okay. Okay. The reason why I'm going to cover neural nets. Let's say it straight up. The reason why I'm going to cover neural nets. I'm going to cover neural nets because they are very popular. They can also be used for classification and regression. Let's drink some water because up there it's raining a lot. Okay, neural nets can be used for classification and regression. Okay, something that I have to mention is that neural nets are becoming too popular. Okay, and sometimes they are overused. There are a lot of cases where you don't use neural net. Okay, if sometimes you use a neural net, it's an overkill. It's an overkill, in fact, because it's an advanced tool and sometimes you don't need it. It's an overkill sometimes because it is an advanced tool and sometimes you don't need it. There are plenty of other models that can also do classification and regression. Okay, boom. Okay, Oula, I don't know what. I'm not there. I'm there. Sometimes the simpler model, the better. you don't want because you are predicting your training data set. Okay, there are plenty of other models that can do classification and regression, and sometimes the simpler the model, the better. And the reason for that is because you don't want something that is so good at predicting your training data set that it's not good at generalizing. Okay, we can say we can we can do a thing like that. Like, okay, generalizing is important in machine learning. We can write that. Basically, it's that because there's so many times where they talk about generalizing. It's incredible. Okay, I will ask ChatGPT why. Why generalizing? Why generalizing is important in machine learning? Why it is important, ChatGPT? Okay. Why generalizing is important in machine learning? Why? Say it. Say it, bro. Oh, okay. Generalization is important in machine learning because the ultimate goal is to create a model that can make accurate predictions on new unseen data. During the training process, the model is exposed to a certain set of examples and it learns to make predictions based on patterns in this data. However, if the model only memorizes the specific example it has seen, it will not perform well on new unseen data. Generalization refers to the ability of the model to make predictions on new data that it has not seen before. A model that generalizes well will perform well on a wide range of inputs, not just the specific examples it was trained on. A good generalization is important for a lot of applications. For example, in medical field, a model that generalizes well on new patient data and predict the disease correctly is important for patients' health and also for the implementation of the model in the real world. Okay, we got it now. We know why it's important. We want a model that can generalize. Yes, we want a model that can generalize. I mean, I make. We want a model that can generalize. I mean, I put a lot of things like that. Okay, let's go. You don't. Okay. Of neural networks are a black box. Neural networks are a black box, and it's not good. Um, things with neural networks is that there are a black box. Okay, the people who create the neural networks will know what is going on inside the network. When you look at some of these other models, when you look at other types of models in machine learning, those might be a little more transparent than neural networks. Okay, with the neural networks, you just have these networks with a ton of parameters, and sometimes you cannot really explain why certain parameters are high. Yeah, and the world question behind why we are going to talk about neural networks anyway. Okay, but we are going to talk about neural networks anyway. People are a great tool for classification and for regression. What's up? What's up, Uncle Grant Cardone? I love this guy. I love this guy. Trust me, I love this guy. 10x baby. 10x baby. 10x. Okay, there, there are a ton of different machine learning models. As I have mentioned, there are a ton of different machine learning models. The top left is called a random forest. The bottom one is classic linear regression. Okay. The top right is called a support vector machine. And these different types of models have their pros and cons. Okay, let's talk about neural networks. I've already searched about neural network in this lesson. We have 81 pages. We have 81 pages of information on this. Well, let's talk about neural networks. Yeah. This is what a neural network looks like. This is how a neural network looks like. You have your input, they go to some layer of neurons, and you have some sort, and you have some sort of output. Let's take a closer look at some of these neurons and let's see what is going on. Um, let's figure. Okay, at one of these neurons. Okay. Okay, let's take a closer look at one of these neurons and let's see what's going on. Okay. 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 A look at a neuron. Basically, like a look at a neuron. Let's talk. Okay, it's in this. A look at a neuron. Let's go. As I have just mentioned, um, we have all the inputs. All the inputs. These are our features. Remember how we talked about feature vectors. This would be a feature vector with n different feature. Okay, okay. A feature vector with n different feature. A feature vector. Okay, each value. Now each of these values is multiplied by a weight by a weight. So that's the first thing that happens. You multiply. Yeah, input. Wait. No, okay. Multiply the value by some weight. Okay. Multiply the value by some weight. Okay. So here are the feature vector with different feature. Okay. Here are different features. Here are the weight. Here all this weight go into a neuron. And this neuron sums up all this weight with value. Okay. Okay, boom, boom. Yes. And then you add a bias to it. This is just some numbers that you add in addition of some the sum product of all of this. Okay. Of all this was the bias goes into an activation function. Before we pass it on. Okay, this is the output. Okay, an activation function is just some function that will take this output and iterate a little bit before passing on. This is the output of a single neuron. Okay, so it's only one neuron here. It's crazy. It's crazy. It's crazy. It's crazy, bro. It's crazy. A bunch of neurons together. Once you have bunch of these neurons together, they form neural. The activation function. This is another example of a neural net. This is what a neural network would look like. You have input, they go into these layers, and then you have another layer, and then you have output. The reason let's drink some. The reason why we the reason why a non-linear activation function. Okay. Okay, I'm trying to figure this out because it's then okay. Okay. All of this and this and okay. Let's try to do it right though. Okay, boom. Into this. Let's figure this out. Okay. If it the reason okay. Attends. Let's figure this out. I'm trying to figure this out. It's because yeah, into this. I'm really trying to make it clear. Then the input into this. This will also just be what we can do. It's essentially propagate this weight on here. Okay, I get it. Um, okay, let me figure this out. Oh, okay. Um, oh shit. Okay. Let me stop ChatGPT because I have another question to ask him. Um, what is a linear function? What is a linear function? Uh, linear function. Tell me what is a linear function, bro. Okay. What is a linear function? I will figure of it now out. What is a linear function? Okay. Let's say here a linear function is a mathematical function that describes a, a linear relationship between two variables. The equation of a linear function is in the form of y mx. What is a linear relationship? What is a linear relationship? A linear function is a mathematical function that describes a linear relationship between two variables. The equation of linear function is of the form y equal mx plus b, where x and the y are the variables, m is the slope of the line, and b is the y-intercept between that can be described by a linear function. In a linear relationship, the change in the value of one variable is the change in the value of the other variable. That the ratio of the change is always constant. For example, if the value of x is increased by a certain amount, the value of y. Okay, so is linear function. Okay, what is a linear relationship? What is a linear relationship? So it means, does it mean that linear functions are pure functions? Oh, that's a. I'm making links here. I'm making links. Does it means does it mean linear functions are pure functions? In yes, I don't know if he will be able to really answer me on that. A pure function is mathematical function that always produces the same output when given the same input without causing any side effect. Linear functions are mathematical functions that have a specific form y equal mx plus b, which describe a linear relationship between two variables. Linear functions are deterministic and have no randomness, which means they are pure functions. Incredible. I understand that. Okay. That not all pure functions are linear. Okay. Not all pure functions are linear, but all linear functions are pure. Are linear functions pure functions? Okay, I get it. I get it. I get it. Okay, 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 okay. Get it. I get it. So just be a sum of some weight plus values. What we can do is essentially propagate this weight on here. And this entire network will just be a linear regression. I'm not going to do the math here because it involves some algebra. But if it's something that you are interested in proving, it would be a really good exercise. Be a really good exercise. Exercise. Okay. To prove that if you don't have a non-linear activation function, then the neural network just becomes a linear function. Okay. Activation functions. Activation functions are nonlinear in machine learning. Okay, I will ask ChatGPT why. Why? Why activation functions are non-linear in machine learning? Tell me, bro. Why activation functions are non-linear? Activation functions are used in machine learning to introduce nonlinearity into neural networks. Neural networks composed of layers of artificial neurons are able to approximate any function, but without nonlinearity, they can only model linear function. So to model complex nonlinear relationships between inputs and outputs, activation functions are added to the neurons. This function introduces nonlinearity by transforming the input signal in a nonlinear way before it is passed to the next layer of the networks. Hmm. Okay, 5 seconds. Just I note something I have in my head. I need to note it before I forget about it. Okay, let's go. Do-do-do-do-do-do. Hmm. Okay, let's go. 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 Okay. Activation. Okay, I get it. We are trying in machine learning. We are trying to avoid linear function. In machine learning, we are trying. Okay, I get it. If it was a linear function every time, uh, it would be a pure function. So to every input, there will be a specified output. We are trying to avoid linear function. If it was a linear function, a machine learning model would be a pure function. We machine learning, we are trying to avoid a linear function. Okay, why we are trying to avoid linear functions in machine learning? Let's go, let's go, let's go, let's go. Tell me. Try to avoid using linear function because they are not expressive enough to model complex nonlinear relationship between inputs and outputs. Linear function can only model straight line relationships which are not powerful enough to capture the complexity of, for example, about to model a nonlinear relationship between the temperature and, for example, a linear function will not be able to model a nonlinear relationship between the temperature. Okay, I get it. So is machine learning just functions, linear and nonlinear? Because at the end of the day, it looks like it's just that. Is machine learning just functions, linear and nonlinear? Just linear function and nonlinear function. It looks like it's just that. Is machine learning just linear functions and nonlinear and nonlinear functions? At the end of the day, it looks like it's that. Machine learning is a broad field that encompasses a wide range of techniques and linear. Oh, okay. And linear functions and linear and nonlinear functions are just a small part of it. While linear and nonlinear functions are commonly used in machine learning, there are other techniques that are also used, just such as decision trees, random forests, k-nearest neighbors, support vector machines, and deep learning. Linear functions such as linear regression, which model the relationship between um, a dependent variable and one or more independent variables, are commonly used in supervised learning, a branch of machine learning where the goal is to learn model from label data that can be used for the prediction. Nonlinear functions such as those provided by activation function neural networks are commonly used in deep learning, a subfield of machine learning that involves training large neural networks to perform a wide range of tasks. Additionally, there are other techniques that are not based on linear or nonlinear functions, such as clustering and anomaly detection, which are used in unsupervised learning, a branch of machine learning where the goal is to find patterns in unlabeled data. In summary, machine learning is a different field that uses a variety of techniques to model complex relationships and make prediction. Linear and nonlinear functions are just a part of it. Okay, I respect it. I was not sure about it. If it was a linear function machine learning model will be a pure function and make the same prediction every time. And make the same prediction every time. Tell me about it. If um, if a machine learning model was based on a linear function and all the input data used to train the model is deterministic and the model is trained to converge, then it will be a pure function and make the same prediction every time it is given the same input. However, in practice, most real-world machine learning models are not based solely on linear function and are not pure function. Even if a linear function is used, As the basic building block of a machine learning model, it is often combined with other techniques such as regularization, feature scaling, and nonlinear activation functions to improve the model's performance and generalization ability. In addition, many real-world datasets have noise, missing data, and outliers, which can make the training process and predictions uncertain. Also, in some cases, the input data is not deterministic. For example, when the input data contains randomness or noise, in this case, the model's output will be different every time it is given the same input. In summary, with a linear function, while a linear function can be a pure function, most machine learning models are not based solely on linear function and not pure function. Okay, what is randomness in data? I have so many questions right now. What is randomness in data? What is noise in data? Hmm. What is randomness in data? What is noise in data? Okay, let's go. Let's figure this out. What is randomness? Tell me, bro. Tell me what it is. Randomness in data refers to variation in data that cannot be predicted or explained by the underlying patterns or models. Randomness can be introduced by many factors such as measurement errors, natural variability, or stochastic. Refers to variation that cannot be predicted. There are different ways to introduce randomness. One way is through stochastic processes, which are processes that generate random outcomes. For example, hmm, natural systems such as weather um, can change randomly over time to the complex interactions of various atmospheric and oceanic processes. Another way to introduce the randomness in data is through measurement error, which can occur due to the limitation of the measurement equipment or the presence of noise in the signal. Okay, it's so good. It's so good. I will know so. I will know a lot about all of this. Okay, what is noise in data? Oh, I have another question. What is the difference between noise in data and um, randomness in data? What is the difference between noise in data and randomness in data? Okay. What is noise in data? Tell me, bro. Tell me. Come on, bro. Noise in data refers to unwanted variations or errors in the data that can be caused by various sources such as measurement errors, sensor noise, interference from other sources. Noise can make it more difficult to extract meaningful information from the data and can also affect the performance of machine learning models. Noise can be additive or multiplicative. Additive noise is added to the signal and can be white noise, which is random noise with a constant multiplicative and modify the signal can be caused by noise. Noise can be independent of the signal, can be correlated with, or it can, in some cases, the noise is known and can be measured in other cases. And then can be treated. There are different techniques that can be used to reduce. Okay, multiplicative or additive, and can be white noise with, yeah, um, noise in the refers to unwanted variation. The Okay. What is the difference between noise in data and randomness in data? But distinct concept. Noise in data refers to unwanted variation area in the data that can be caused by fair use, can make it more difficult to extract meaningful information. Hmm. C'est pas bon signe si tu veux. Okay, I have everything now. I have everything. Are related but distinct, recognizing that every unwanted variation in the data can be caused by various sources such as measurement, errors, sensor noise, or interference from other noise. Randomness in the data refers to variation that cannot be predicted and explained by the underlying pattern or models. Okay, let's make a pause. It's been 2 hours. I'm here. And we have 1 hour left in the video. And we'll finish this video. I think we'll finish this video tonight in the 4 following hours. So let's make some pause and I will come back to it. Let's do some pause, okay, commentary. Okay, boom, boom. Putain, je retrouve plus où c'est. I don't find. I had difficulties to find the sound. Let's go. We're back. We're back. We're back live. Let's go. Let's finish this. I have such an in-depth explanation of machine learning. It's crazy. Thanks to FreeCAD and ChatGPT. It's crazy. What I need to do is take all these things here. I will put it. I will put it at the top of the lesson somewhere. Somewhere at the top of the lesson. Here. I already have 96 pages of information. It's crazy. That is what we are trying to avoid. Avoid. Oh, yeah, neural network. We would just use a linear function. Without activation functions, this becomes a linear model. Okay. Examples of activation functions or no? Let's talk and look at the activation function. Okay. Examples of activation function. These are the kind of activation function that I'm talking about. There are more than this, but these are the three. Okay, three. Very at the left is a sigmoid activation function. It goes from okay. It goes from 0 to 1. Okay. At the center. Activation function goes from -1 to 1 below. Activation. Below activation function, probably the most popular one. what happens here is if the value where zero, it's just room, and if it decreases, zero. What happens in each? Of an activation when you put it in. Okay, that's the point of an activation function. When you put it in the very end of the neuron, this makes the output of a neuron nonlinear. Okay, okay. So with activation function, neural networks are nonlinear. So um, we our activation function, the only thing that makes uh, machine learning neural networks nonlinear. That's a really good question, though. Okay, activation function are a key component that introduce nonlinearity into neural networks, but they are not the only thing that makes neural networks nonlinear. Neural networks are composed of multiple layers of artificial neurons, and each layer can transform the input in a different way. Each layer can have a different set of weights and biases, which can introduce nonlinearity into the network by stacking multiple layers with nonlinear. And okay, activation function are a key component that introduce nonlinearity into neural network. But the architecture of the network and the combination of different type of layers and weight and biases also introduce non-linearity. Neural networks are able to learn complex nonlinear relationships between input and output by stacking multiple layers with non-linear activation functions and using architectures that are specifically designed to exploit non-linearity in the. Okay, it's interesting. It is interesting. It is really interesting, though. We have seen this picture before. That's I will call it like that. We have seen this. Um, Training set that goes into our mode, and then we calculate some loss. Okay, let's go. And then we make adjustments. And okay, that this is what our L2 loss function looks like. If you from 2 minutes, it's a quadratic function. And when your real and predicted value are further apart, then the square of the difference becomes really large. And yeah, plus. And all okay. Up in the air, up here, error is really large. So when you have um, a loss of 8, the error is really large because is it multiplied by itself? I don't know. Okay. Up here, the error is large. We want to decrease the loss. a loss. The smaller the loss, the better our model is performing. Loss is just a metric to assess how well our model is performing. So our goal is to get close to zero. Is to get close to zero in loss in loss. Okay. Here here is a part that might involve a little bit more calculus understanding, but not because anybody out there knows calculus. I will skip. Not skip. Not everybody out there knows calculus. Keep the numbers and just if we are up here. Um, okay, there's one thing I should do though. I should. I just write something. I have a note. I think I should make a video on a function. I should make a video on functions because there is a lot of functions in this machine learning thing. It's incredible. I should make a video where I study function. Make a video where I study functions because there is a lot of functions in this machine learning thing. Okay, there is an incredible amount of function here. It's crazy. It's crazy to the point where. Okay, let me come back to this. I'm just trying to figure out something though. Hmm. Okay, I will see that later. Yes, of course, yeah. Okay, if we want to go close to zero, we want get in the opposite direction. Direction. The higher we go, more we want to step. Okay, yeah, maybe, yeah, because the further away We are from our goal, whereas maybe here we want to take baby steps. We want to take baby. First, we don't want to overshoot. We don't want to pass and never be able to find it. Okay, okay, sense. So we use something called gradient descent. And gradient descent is basically measuring. Okay, but will help us. Okay, so we use something called gradient descent in the case, and gradient in this case, and gradient descent is basically taking it's measuring to some extent the slope at the given point is taking a step in the direction of okay, gradient descent. You can call it like that. Gradient descent. Okay. Okay. Back propagation. Propagation is the reason why neural networks. I will keep it there, but I will go up. Come on, bro. Okay. Okay. I want to understand why back propagation is the reason. Why back back propagation is the reason neural networks work. Network. Neural networks. Neural network work. Okay. Why back propagation? Okay. Why back propagation is the reason why neural networks work. Back propagation. Back propagation is the method used to train neural network. It is used to calculate the error at the output of the networks and propagate it back through the network to adjust the weights of the neurons. This allows the network to learn and improve its accuracy over time. It is considered the reason why neural network work because it is a powerful algorithm that allows the network to learn and improve through training. Without back propagation, neural network will not be able to learn and improve in the same way. Add to loss function. Okay, if we take a look at, okay, she speaks a lot right now. Take a look at this M2 function. I think. Okay, I will try to understand what you say. You might think it depends of what or wherever you are. Okay, y values are predictive values, and real values. Our real values always stay the same, yeah, because our values on the data set will stay the same because they are based on the data set. A predictive value is a function of all the weights we just talked about. Mm, mm, mhm. But our inputs are also and are staying the same. So as we invest, enfin, deux options d'admin, c'est soit coucher avec James, Okay. Okay, let's go. 2 seconds, please. My, oh, no, my. Okay. Mhm. By looking in the various way, no, mhm. To be honest, the mathematical explanation, I don't know. Okay. Okay. So what we're going to do is set a new weight for that parameter, and the value is going to some alpha. Think of this as some variable multiplied by think of this as some variable multiplied by this value. Okay, I get it. Okay, so basically we can say backpropagation is basically a step where we give new weight to the neural network. So is backpropagation a step where we give well to the neural network. Okay, let's go here. Okay, basically, okay, that. Okay, understand it. Yes, backpropagation is a step in which new weights are given to the neural networks. The process of backpropagation involves the calculation of the error at the output network and then using the error to adjust the weight of the neurons in the network. Hmm. Okay. Okay. Mm-hmm. Mm-hmm. 3 hours. Friday. A quick side note. If system machine learning is smart okay. If that confuses you. Right. I don't know. So okay. Is Jen with respect us to take in that direction. this value alpha here is what is called uh, turning rate. Wait, no, no. Every single uh, huge. Then we want to take baby step, and if every is telling us to go in one direction, and five are going in that direction. Okay, let's go. Okay, going back. You can see uh, wait, it's getting updated daily with respect value. The gradient with respect. Okay, my brain is like trying to recall all this information. Crazy. Let's go. Let's go. There is 1 hour left. Let's go. Okay. That is how back propagation works. Propagation. This was our crash course on neural networks. This was not the most comprehensive course in neural network. If you are interested by neural network, encourage your developer into the mathematics of it. Okay, how to implement neural network in code. This is where libraries, machine learning reference among we often need to implement a model. And if we want our model to be a neural like this, we can go and code our neural, but we don't want to start from scratch. But we don't start from scratch. Bring a lot of good using that type of language to that have been developed and optimized. Okay, this moment. Okay, use a library called then neural like this. try to go through and develop the network entirely from scratch. Okay, I get it. TensorFlow. Okay, okay, okay. TensorFlow is an open source library. Okay. Okay. TensorFlow is a library that comprises a lot of modules. Yeah, that's it. For example, we might have this module here. For example, we might have a bunch of tools to import data, and keep data consistent and visible. Uh, it will will API is carried. Okay. Okay, another thing is Keras. So here we have a bunch of that will help create models and help us optimize them, help us optimize them. These are the optimal line of this. We want to use these packages and these libraries because uh, they were Learning. So, like, so we could collab. Let's go. 50 minutes later, we are beginning to code. Oh, it's incredible. 50 minutes of preparation just to code, bro. It's incredible. We deserve it. We deserve it. We're not stealing this, bro. We are not stealing this. Let's go. Let's go. Okay. To the answer. Lord. Okay, that's good. That's good. That's good. One thing I want to do though. There is one thing I want to do though. I want to be offline. Um, yes. Boom. Fuck the online, bro. I want to be offline. Let's go. Let's go. Let's go. So another had to plan and non-neutral using text. Okay. Oh, she has changed clothes. Not that we have. It's another day. It looks like it looks like it's another day though. Like it looks like there it's night time and now it's daytime based on the lighting. I don't know why I'm saying. And she has changed her hair too. Around. So let's try to implement it. Okay, one. Let's go. One. Create a new notebook. Name it. Name it whatever, but name it here. It forward an example. Okay. Again, use the same inputs that we have already used. and run this. Now, the second thing that I will have import is the set. Okay, let's go. Maybe it's drag it left of Google Colab, Google Colab, and now it is there. Boom, 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 boom. There. It is indeed so the set that we're using here is Hibernate that is originally from the National Institute. That is okay. All all the instances, all in this data set of again is a lot of features, but the final feature is whether or not there is. Let's look at the set. The first thing we can is to create. Okay, so we are going with CSV. Now we can just say libraries. So we should, let's see, blood pressure. Yes. Bunch of other measurements. Okay. Data visualization. Okay. Okay. One. It's always a good idea to do some. Any of these. Um, there are many different. You can try to find for each. Yeah, and what I'm going to do. Yeah, it's value of the and then come. Okay, do that. We will do that. We are do that using a follow. for I in range. Then I use the column of the data frame. One pairing against the follow-up here is string run to each column except and that's one. Table here. Okay, add index. Okay, to show you guys how this look like. To show you guys. Is to set with PL C dot east. Okay, run. Okay. this thing. Okay. This basically is the frame where all the outcome are equal to one. Interesting, interesting. So is there any loop? There's no loop. Okay. R will get a frame where all the outcome which means that on the page. And do something. Okay. Okay. This here frame all out. We want to difference. We are doing. And of course, the name. Now let's feed subtitle, which is labeled with empty subtitle. Give it this label. Okay. Show. Okay. Um, so let's run this. What did you like? It's oh, yes. Yeah, I'm sorry. Okay, I don't know the operation she's doing here. She's going to say density go through and pins 15. Okay. For a second. But let's say it's ratio minus 2. We have more visualization. Okay. It's Okay. Okay. Sure. Okay. We will split into a training and test that. It's been so long that I'm focusing on this that my brain is beginning to be less focused. Splitting that. This function here. Allows us to split arrays matrices. What? Oh, first we so let's from okay scalar input make sure so here And um, uh, uh, do this. And this. Yes. Okay, we are good. Yes. Okay, I'm trying to figure out one thing. Is it different from what is different in this course? In this one? Okay. Okay, so in this course, it gives multiple implement. Okay. Okay, I'm getting it. Okay, okay. I think I will make a pause. I'll make a bit of a pause though. 4 hours of life though. It's a lot. Let's pause this.